Hello, and welcome to the second of two videos in quantitative reasoning on more advanced set operations, complement, union, intersection, and combined operations. In the second part, we also looked at Cartesian product in the last video. In the second part, we're going to look at how can we show what an operation would be if we don't actually have the set written out, but if we have instead a Venn diagram that represents the set. I'm not sure where I drew that there. Let me erase that. Okay, so suppose we have a Venn diagram of two sets A and B. Now you can represent a set by an area on a piece of paper, and usually in Venn diagrams we use a circle for that set. So there's set A. The space in the circle represents the things in set A. The area in the circle is set A. So then we can also draw another circle for set B, and it's pretty standard when you have two sets. The two-circle Venn diagram goes something like this, where they have a section that overlaps. This overlap might be empty. If the sets are disjoint and have nothing in common, this overlap in the middle here will be empty. But if they have sets in common, it will go in there. So, let's continue on here. So we have, this is set B. Okay. So how can we find expressions involving A and B such as A? Now this symbol here is the union, A joined together. This is the intersection, or A complement in union with B. I'm going to start doing this on this slide. They didn't leave me enough room on the next slides to finish this, but let me do, what if I want to represent A in union with B? I'm going to shade in everything that's A in union with B. So it's everything that's in B, so this whole area that's in this red circle. And along with including the intersection, so everything that's in A. So A in union with B will look like this on a Venn diagram. These circles will be shaded in. I don't want to shade too much because I tend to go outside. I don't color in the lines very well. But you would shade in these two circles and nothing outside of them because you only want to shade in what's in the set. So these whole circles are shaded. If you see that, assume the whole thing is shaded. That is A in union with B. That is a good visual representation from a Venn diagram. Now, what if I wanted A intersect B? Let me see. I don't know that I can just erase that part. Oh yeah, maybe I can. There we go. I can. So there, I've erased A in union with B, and I'm going to do A intersect B next. So I like the highlighter for doing this, but I'm going to pick a different color. We're going to do A intersect B in yellow. A intersect B is where they have something in common, so where they share a space. So the circle for B and the circle for A actually share this space here. It's this little oval in the middle. That oval in the middle will be A intersect B. And every time you have the intersection between two sets, even on a three-set Venn diagram, which we'll see come in another week or so, the intersection between two sets is always an oval, the way you draw them. Because even if you drew a third set in here, and I'm saying this for you so you remember when we get there. If I draw some set C, if you drew set C, you would make it so it has some overlap of just A, some overlap of just B. This part right here would be A intersect B intersect C, but it's still part of this A intersect B. So I know we haven't gotten to three-set Venn diagrams yet, but if we do, that's what you would be doing with it. Oh, I thought I picked up the eraser. I did not. There we go. I kind of like the way this erases. All right, so A intersect B is the space in the middle here. Now, this one's a little more complicated. I'm going to actually erase some more of these things. I just want to keep the circles, basically. Oh, I erased my circles. Never mind, I should have just erased the whole thing. All right, I'm going to redraw my circles. I have circle A. Is there. Circle B, it's not as pretty as my first one was, is here. Need to overlap them. B is in red. Now I want A complement intersect B. Well, A complement is everything outside of A. Now, what this hasn't shown is the universal set. I'm going to draw in the universal set here. I am on a rectangle that is my universal set. So anything in this rectangle is in the universal set. So A complement is everything outside of A. So A complement would be everything, including stuff outside of B. Everything that's in B, but not in the intersection, because the things in the intersection are in A. So the complement is everything outside of this circle, and I'm not going to be doing a thorough job of shading it in, but you can see the places I don't shade in are inside the blue circle for A. Everything that's not in either A or B is out here. Everything that's in just B, but not A, is like over in this crescent-shaped piece. The stuff in the middle here is in set A, so I don't shade that if I'm shading A complement. I want the things not in A. A complement is like the opposite of A, everything not in A, like the negative of A. So I want to know where that yellow intersects with B. So that's where the yellow part overlaps with the circle for B. And when I see that, I see this space right here. I have yellow there. Notice you can see the difference in the pink. It's kind of cool the way it colors in. So as I color in here, I get all this red. So the B, I'm making set B in pink, but the pink plus the yellow makes this red. This is the complement of A, everything outside of A, intersecting with B. So not the yellow, but this red and pink part here. And if I shaded in there, it would be shading in B in pink. But so this area where I see this red, the whole crescent shaped here. I find A complement, and then where B overlays A complement. Now I don't pick this space here because it's A, clearly, and I don't pick this space here because I'm still in A. That is in B, but I want everything that's outside of A. So the two constraints on the part I'm going to shade, it has to be outside of circle A, and it has to be inside of circle B. That's what both of those things have to be true. If this were the union, it would have to be outside of circle A or inside of circle B, and then I would have joined it because it's a bigger set when you do a union. But the intersection is just the part that's shaded, that's A complement, and the part that's shaded, that's B, where we shade for both of them. This red area in here is the complement of A was in yellow, and then where that overlaps B is I just shade on top of wherever the yellow lies on top of the B. I get the complement of A intersecting B. So that's how you could show a Venn diagram in general to show a set operation. You can use a Venn diagram to show a set operation in general terms. All right, so this is asking us to do the same thing, and honestly, I think what I did in the last slide was better because I showed you the universal set. This isn't quite complete, but the thing that is useful in this is if you're just talking about sets A and B, if you look over here, I seem to have lost my pen. There we go. If you look at this, the stuff they've outlined in red, that whole outline, everything in that outline, sets A and union would be, it'd be everything in this outlined part here. Okay, the two circles all colored in. A intersect B will only be this green part here. A complement would only be this blue part here, and if you had the universal set, it is also out there. Students tend to forget that if you had a universal set there, that anything not in B is also, anything not in A or B, anything that's written out here is also not in A. But you just include this part of B that's highlighted in red, and then the rest of everything that's outside the two circles. The slide didn't do a good job of showing you that with the universal set, so I changed it up when I did the last one. So here, little different situation. I have a diagram with elements filled in. I want to find A complement intersect B. So A complement is everything outside of A. So the 5, the 8, the 3, the 6 are all inside of this red circle. So A complement, I write that down. It's just the set containing 9 and 2. Those are the elements, 9, 2, just these two here. So that's A complement. In this case, A complement intersect B. Well, the set of elements in B of 3, 6, 9, 2, the intersection will be the same thing. Now, if I had had the number 7 out here in the universal set, wasn't in A, wasn't in B, this would have included a 7, but this would not have because it's not in B. So this joins together the complement in set B where they overlap. If the complement included the 7, it does not. So here would be the 3 things in your complement if you had a universal set. Only the things that are in B stay in the intersection because you're asked to intersect it with B. The other thing I want you to notice in this slide, and this leads into the next thing that comes up here, is how many elements are in the union. So we're going to erase all this stuff. You can always rewind the video and then stop it if you're taking notes if this is too fast. So I'm going to erase all that stuff. And we're going to look at the number of elements, the cardinal number, the number of elements in A in union with B. And I believe this is how your book writes card. This is just the number of elements in the union of A with B. So you make one big set out of these circles. So if I count them, there's 1, 2, 3, 4, 5, 6. The 6, that's easy enough to count. Well, how many elements are in A? Well, it'd be 1, 2, 3, 4. And how many elements are in B? Again, 1, 2, 3, 4, because the stuff in here is in A and the stuff in here is in B. So there's 4. If I add that up, I get 8. So if you just add the number of elements in A and number of elements in B, it does not give you the number of elements in the union. If I look at the intersection of A with B, there are 2 elements. So what I have to do is add up the number of elements in A. To find the number of elements in the union, I have to add up the number of elements in A plus the number of elements in B and subtract off the number of elements in the intersection. Because I've counted them in A, when I go to count them again in B, I count them twice, so I have to subtract them off once. So if you did 4 plus 4 minus 2, you would get 6, which indeed is the number of elements you see in this union. So that's the law of inclusion-exclusion, actually. You include it once, but exclude it the second time when you count it. Those are the big ideas I want to get across for this. This video is the idea of drawing the Venn diagrams and shading to show an operation on a set, and how do I figure out the cardinal number of the union of 2 sets. So this slide goes more into that cardinality of the set, the cardinality of a finite set. So one book I'm using uses this. Remember absolute value? Like if the absolute value of -3 is just the number 3 because you don't care which direction it goes in, you just care how big. In general, when you see these straight line bars around something in math, it kind of means the size of the thing. That's pretty general. That's what that means throughout several math classes I've taken. That means if you do this and there's a complex number in there, you're asking how long that number is if you drew it in a complex plane. Or the philosophy language-based study of sets uses this number of elements in A as a symbol. And I think this might be more what your book uses, but be aware that this absolute value, if there's a set inside, it's just asking you how many things are in the set. So if I want to know how many things are in 2 sets put together, how many elements do I have in the union? I add the number of elements in each set, but I have to subtract off how many things are in common because I've counted those things in A and I've counted them in B, but I only want to count them once. So if I just do number of elements in A plus number of elements in B, the elements that are in both have been counted twice. So I subtract off how many elements are in both so that now I'm only counting them once. That is how you determine the cardinal number of a union of 2 finite sets, meaning you can find the cardinal number of A and the cardinal number of B and the cardinal number of the intersection. We won't be doing this with infinite sets. That doesn't really make any sense in the context of this course. So here's a practice problem. A is 1, 4, 5, 6, 7. B is 4, 5, 6. What is the cardinality of B? Well, that's just how many elements are in B. So there's 1, 2, 3 elements. The other way this could be asked is you could be asked what looks like the absolute value of B, or I could just say what is n of B, rather than spell out the word cardinality, either of these symbols. Cardinality of B is 3. Now, they give us the same two sets and want to know the cardinality of the union. Well, there's 1, 2, 3, 4, 5 things in A and 3 things in B. And what's in the intersection? So A intersect B is, I start with the biggest set. Well, actually, you can start with the smallest set. It makes more sense. So is there a 4 in A? Yeah, there is. I need the set symbol. Is there a 5 in A? Yeah, there is. So I'm checking each element of B. Is there a 6 in A? Yeah, there is. Actually, everything. B is actually a subset of A, is what we would say. But for the purpose of this problem, I need to know how many things are there. That's 3. So I do the number of elements in A plus the number of elements in B. Cardinality of A plus cardinality of B minus the number of elements in the intersection. And what I get is 5 plus 3 minus 3, or just 5. So sometimes we make the union of two sets. If one set is a subset of the other, you don't make the set any bigger. The union of these of A and B is actually just set A in this case. Okay, so you'll get some more practice with that in the homework. Email me if you have any questions.